All right, so this is the last topic for Unit 8, 8.10, buffering capacity. So the objective, explain the relationship between the buffer capacity of a solution and the relative concentrations of the conjugate acid and conjugate base components of the solution. So buffer capacity, it is the term that is given to the amount of acid or base that can be added to a buffer system without changing the pH by more than a pH of 1. To be able to increase the capacity of a buffer, you should increase the concentrations of the conjugate acid-base pair in the same ratio. This keeps the pH of the buffer the same, but that means that there are more moles of the conjugate acid-base pair available to react with any base or acid that is going to be added. So let's look at the following buffers. We're going to consider the following three buffers, and then it's going to have different concentrations of acetic acid and sodium acetate. Acetic acid is my weak acid, and that is my pKa is going to be 4.76, kind of like the last couple of videos. Buffer A has a 0.100 molar solution of both of my acetic acid and my sodium acetate. So hopefully you can remember now, my pKa is 4.76 for my acid, for my weak acid. So assuming that I have 1 mole, 1.1 mole of each of my HA, if you will, and this will be my A minus. Luckily, it's a 1-to-1 ratio. So my moles for this, well, it gives you the molarity. So because it's a 0.1 molar solution of sodium acetate, my acetate ion, the concentration is also going to be 0.100 molar. So I plug that in like before, and my pH is going to be 4.76. So kind of like we did a couple of topics ago, we had some change in our buffer. So here we are adding 0.050 moles of NaOH is added, and we're going to assume there's no volume change. It will react with the acid, and it's going to affect our equilibrium, so to speak. So by adding some hydroxide ion, and it's going to be 0.050 moles of that, or molar of that, and my O is going to drop to 0. I don't know why I had a weird pause. So remember, the reaction this is the reactant side, and then the product side is on the other side. So that means that these two, the acetic acid and the sodium acetate, are going to drop by 0.050, and that means my equilibrium, my concentration for the acetic acid is 0.050 molar. My conjugate base, when it adds, it's going to be 0.150. So essentially what we're going to do is find out what our new pH is with these different concentrations. So we're going to plug in our pKa 4.76 plus the log of my conjugate base divided by the concentration of the acetic acid after the fact. We do our work, we end up with a pH of 5.24. So that's buffer A. Oops, my bad. Ooh. Poor production quality. Buffer B has a 1 molar solution of each acetic acid and sodium acetate. So same process. Luckily, because it's the same concentration of each, my pH is going to equal my pKa of 4.76 again. If 0.050 moles of NaOH is added and there's no volume change, how is this going to affect it? So before we added 0.050, we're also actually adding 0.050 again, but our concentrations are a little bit stronger, 0.1 to 1.00. So notice that the change is actually not that much. So subtracting out the 0.050 moles, like again here, we're going to assume we have 0 because it's a strong acid, it's a limiting reactant, it's going to get used up. So then my conjugate base increases to 1.05, my acetic acid will decrease to 0.95. Then I'm going to plug in my numbers again over here, and this will give me, calculation-wise, a pH of 4.80. So the buffer with a higher concentration resists a change to pH better. It resists better if there's more of it to work with, so to speak. So by having a stronger molarity for both, it's more likely to resist the change in pH, if that kind of makes sense. Now we have to look, of course, got to make it harder. Why? Because why not? We have a buffer solution, or buffer system, I'm sorry. We have unequal concentrations of my acetic acid and my sodium acetate, my conjugate base. So same process, I plug in to my HH equation. I end up with a pH of 5.76 when I do the calculations. Same process, if I'm adding 0.050 moles of NaOH, notice how it changes here. It decreases down to 0 again, similar concept. The concentrations are affected here. So my 0.1 molar drops down to 0.050 molar acetic acid, and my conjugate base will drop down to, will increase, because it's the same over here, will increase to 1.050. Interesting. So then I plug in notice when I plug in my equilibrium stuff in here, the conjugate base and the acid, same process. Look at how my pH changes. 5.76, well, it originally changed, it was like 4.76 when it was equal concentrations. Now it's 5.76, and then it increases to 6.08. So the change from the original buffer is 0.32. If 0.050 moles of HCl is added to the solution, now it's going to be a little bit different. So remember we said that if you add acid, it's going to react with the conjugate base to form the acid again. So this is not a products over reactants thing, just a reminder of that. It is a conjugate base over the acid concentration. So that's something you need to be able to remember. So again, 0.050 moles is added. So that drops down to 0. Your conjugate base will decrease to 0.950. Your acid will increase to 0.150. And then you plug in your numbers. And then your pH is going to be 5.56 after the fact. So the change from the original buffer is about 0.20. Oops. You can see that when a buffer system has a greater ratio of moles moles of the base to moles of the acid, the pH changes less when an acid is added. The opposite is also true. Buffer systems with a greater moles of acid to base will change less when a base is acid. Ugh, ooh, that's bad. Okay. You can see that when the buffer system has a greater ratio of moles, so more moles of base than acid. So the more base you have, the less change in pH you'll have when you add more acid to it. The opposite is true. I don't know if I may get this one right. With a greater ratio, if you have a buffer with more acid than base, there will be a lower change, not as much change of pH if I add base to it. So again, that's the whole point of a buffer, is to resist changes in pH. A buffer is created using 100 mL of 1.00 molar benzoic acid and 200 mL of 1.00 molar sodium benzoate. So there is my conjugate base. The Ka for benzoic acid is 6.4 times 10 to the negative 5. Determine the pH. So remember, this is part A. Calculate the pH. So pH equals pKa plus log of the conjugate base, just make it easier on us, over the conjugate acid. Actually, I'll just make sure we're good. Okay. So we have our Ka, so it's good. So to get the pKa, so pH equals, the negative log of the Ka plus the log of, what are we going to do about this? So we have our sodium benzoate. They give it to us here, again, in a 1-to-1 ratio. Thank the Lord. We need to plug in our concentrations. So the concentration of the benzoate is going to be, let's see, so we got to figure out what the molarity is of this and that. It's ugly. So how are we going to do that? So for the benzoate, it's going to be 0.2 for 3 zeros times 1.00 moles per liter. And that's going to be, so we're clear, 0.2, looks like 3 sig figs moles. And then for the moles of the acetic or the benzoic acid, looks like it's going to be 0.1000 times 1.00 moles per liter, and that's going to be 0.100 moles. So to get my new concentration is a little bit different. Before we just had the full concentration. Now we're actually given volumes. So we're going to divide this by the total volume of these added together, because you're actually given volumes for this. So that means my concentration is going to be 0.667 for my benzoate, that part, the conjugate base, and then 0.333 for my acid. So I need to erase this because I need way more space. So the pH will be approximately 4.19 plus log of 2.00. That will equal, when you do the calculation, 4.49 for my pH of this buffer. Part B. Will the pH of the buffer change more when acid is added or a base is added? By looking at this, here's what we need to focus on for this particular question. We got to look at what's in a greater capacity or greater concentration. So since the conjugate base is greater in concentration in this buffer system, the pH will change more when a base is added. All right. So, if you have any questions with this, please let me know. Kidding. So 3 buffers were created with a weak acid that has a pKa, and then you have lithium and some whatever the anion is. You have a buffer with 1 mole of HA and 0.5 moles of LiA, and they're all dissolved in the same solution. That makes it way easier. You have buffer Y with 0.5 moles of the acid and 1 mole of the conjugate of lithium and the anion. You have buffer Z that has 2 moles of HA and then 4 moles of the lithium and anion. What is the pH of each solution? And then which buffer will be the best at resisting change to the pH? So now instead of just 1 buffer, you have to analyze 3 and determine the pH of each, and then figure out what is the best at resisting change. So when acid is added, that's a specific part. So I'll give you all a minute. Y'all can work on this. All right, so part A. Buffer X, buffer Y, buffer Z. Hopefully, I think you should have enough space for that actually. So luckily for us, it gives us the total amount of solution for these. And from there we can it's really not that bad. So remember that the pH equals pKa plus the log of the conjugate base, over the acid. So pH equals the pKa 3.20 plus the log of the concentration. So we have, this tells us it's all 1 liter, so not that bad. So 0.5 divided by 1, so all of these, the numbers will match up. So it's going to be 0.50, 0.50 over 1.00. I do the calculation for that. I will end up with a pH of about 2.90. pH for Y, it's going to be 3.20 again, plus the log of, let's see, we got 1 for that one, divided by 0.50 for the acid, 3.50. Z pH will equal 3.20 plus the log of 4.00 over 2.00 for my concentration of the conjugate base and the acid. The pH will be also 3.50. Crazy. Which makes sense because of the ratio of the acid and base. Anyway, so letter B. Don't laugh at that either. Which buffer will be best at resisting a change to the pH when an acid is added? So luckily there's all the same molarity, the same volume, so the only thing we're going to be focused on is the number of moles. So what's going to be the best at resisting acid? So technically we didn't even have to answer this, but the best, answer A first, but it's fine, whatever, no big deal. So which buffer will be the best at resisting change to pH when acid is added? So since the answer will be buffer Z, as buffer Z has the highest concentration of the conjugate base, so it's going to resist acid more. All right, now the lecture is over. If you have any questions, please let me know. Thanks.